Hi, everyone. Today we're doing springs. We're going to go over the spring force, and then we'll go over work done by springs and work done on springs. So first, how springs work. Okay, so the spring force is shown as F of S equals negative kx. Okay, the k is a spring constant. We'll talk about in a second, and the x is the distance that the spring is either stretched or contracted from its equilibrium. So this is the force a spring exerts on an object connected to the spring. So K is called the spring constant. What are its units if X is in meters? So if X is measuring the distance from the spring's equilibrium, right? That means, oh, whoops, I gotta connect my pin. So if the spring force equals negative kx, right? We've got a kilogram meter per second squared on this side, right? Because that's a Newton. Oh, whoops, I'm way too low on that. Can't see my barrier there. Kilogram meter per second squared. Then we've got this K unit, and then we've got meters on this side, right? So we can divide out a meter, meaning that we will either have a kilogram per second squared as our unit for K, or you could just call it a Newton per meter. Okay, this is going to be more common when you divide that mass over here, right? So you would have, if you have newtons and meters, the K would show to be a Newton per meter. That's the most common way to see that unit, but a kilogram per second squared is still feasible. Now, if we compare two springs, would the stiffer spring have a higher or lower K constant? So if this F, right, this is the force that a spring is exerting on an object. If you try to press on a spring, if it's stiffer, it's going to put more force on you, right? If it's more flimsy, then it won't resist you as much. There'll be less force and you'd be able to easily move it, right? But if it's stiffer, it's going to resist you with more force. So if there is more force exerting on you, then that means that this K constant needs to be higher for a stiffer spring, which is true. The stiffer the spring, the higher the spring constant. Okay. Now, let's look over at the graph we have over to the side real quick. Okay, so we have this graph over here. Number 2 asks, what does the area under the graph represent? So if we look at this graph real quick, we'll talk about the ones, scenarios up above in a second. So actually, no, let's do these right now. So when we have this spring up top for letter A, okay, X is considered positive when you are stretching the spring, right? Relative to the spring, that is a positive motion to stretch the string. Okay, right there, positive. Relative to the spring, it is negative if you compress the spring. Now, this is, of course, going to be subject to whatever system that you have going. If you're doing summation of forces or later on summation of work, your system can kind of have its own defined positive and negative, right? But relative to the spring, it is traditional to say that X is positive when it is stretched, and the spring force will be directed to the left because it wants to return back to equilibrium. That's what springs want to do, right? And X is negative on a compressed spring, then the spring force would be directed to the right. Because again, a spring always wants to return back to its equilibrium. Now, X is 0 when it is sitting at equilibrium. That is its natural length where it wants to sit, and the spring force will be 0 when you're at that distance. Now, let's look at the graph down here. This is a graph of a spring being moving from contraction over here. Right here, it is it's compressed. Right here, you have a compressed spring, and then it moves over here to be stretched. Right, because being stretched would be a positive x. Here's your positive x. And then being compressed would be your negative x, right? Now, number 2 asks, what does the area under the graph represent? So the area under the graph represents the work done by the spring, right? Work is the area under an F versus X graph. Here we have F versus X. So this area represents the work done by the spring. So as this block that it's connected to, as it moves from a negative x to 0, that you can see is a positive work there. And then as it moves from 0 to some positive x, this would show as a negative work, right? Now, that's not always going to be the case because springs can move in many different directions. But for this time being, this shaded area, right, is going to represent the work done by the spring on the block as it moves from either negative x to 0, or as it moves from 0 to some positive x. Okay? Now, what equation can we use to calculate this work? Okay. Well, what we can do is we can show the integral, right? If we're doing the area under a graph, we're going to do the integral. So if we have the integral of f of s dx, right, that is work done by a spring. This will be from some x naught to x final. So we would do the integral from x naught to x final of negative kx. Okay. So when we do that, you would get negative kx squared over 2 from x naught to x final. Now, what we'll do here is we will plug in our final minus our initial, right? So we have, and we'll actually call this 1/2 kx squared. That over 2 is going to become a 1/2 in a second. So we will say this is negative 1/2 kx final squared minus negative 1/2 kx naught squared, right? So we do final minus initial like we do on all integrals. But this negative, okay, actually makes it more simpler if we were to write 1/2 kx naught squared minus 1/2 kx final squared. Okay, you can see that those equal each other. So you can actually notice that the minus sign can actually flip when you do this. Okay. Now, this also works best as a definite integral. We'll talk about this later. But a spring, if you're going to find the work done by a spring, you've got to have the initial and final measurement. If not, you're not going to get an accurate work or accurate force out of your spring if you don't have specific measurements. Okay? But this is the area that we can use to calculate the area or to calculate the work done by a spring on an object. Good. Now, next, finding work with the F versus X graph of a spring. So here, R, F, and D are in the same direction. So this is the question that we're going to ask ourselves as we go through these scenarios. You can see that we've got 4 kind of complex scenarios that we're going to go through to see, is the work positive or negative? And the real question is F and dr going to agree? The reason we call it dr is because you can say that work is the integral of f dr instead of dx. That's just one way to write that integral. So work done by a spring from compression to equilibrium. So let's look at right? We've got a spring. If it's moving from compression to equilibrium, oh, whoops. We have compression to equilibrium, right? It's compressed, we pushed the spring down, and now it's returning to equilibrium, right? So the force is going to want to return to equilibrium, right? The delta R, or the dr, okay, would also want to return to equilibrium. This is going to give us positive work, right? The force and the displacement agree. That's the rule for work. That gives you positive work. The F is with the delta X. Now, let's say we want to find the work done by the spring from equilibrium to compression. So we start at equilibrium, and now we're moving to compression. So here, this is our dr, right? We are moving from equilibrium and we're compressing it down. But the spring wants to go to equilibrium. So the spring force will actually resist you, right? The spring force is going to want to resist as you push down on the spring. As you compress a spring harder and harder, you've probably played with a spring before. You can, as you compress harder and harder, it resists more and more, right? So that spring is resisting the compression. So here, the force opposes the delta X. So we can see there it's going to be a negative work. The spring is doing negative work when we look at the work done by the spring. Okay. Now, if we will, now we're going to kind of flip the table a little bit. We're going to ask, what is the work done on a spring from equilibrium to compression? So again, we're going from equilibrium to compression, right? Again, dr right here. But we were looking at what is the force done on the spring? Well, to compress it, right, from equilibrium to compression, this is the force done on the spring. That's going to have to push the spring in the same direction, right? So that would actually be positive work done on the spring, not by the spring, but the work being done to the spring is going to be positive because the force and the displacement are going to agree in direction. Now, last one, what is the force done by the spring from equilibrium to expansion? So if we want to go from equilibrium and we are moving out to expansion, what is the force done by the spring? Well, again, the spring always wants to return to equilibrium. So that arrow, the force done by the spring, will always point towards equilibrium. So this is again going to be negative because the force is going to oppose your displacement, right? Now, that's one way that we can represent this just by drawing it and kind of imagining it. Let's look at the graph. We can also see this on the graph. Now, this is going to get a little complicated because we're going to talk about going backwards on a graph. So this is something that your math teacher usually doesn't let you do. But when you get into calculus, sometimes you got to go backwards on an integral. So let's look at the work done by, let's look at the first one. Work done by a spring from compression to equilibrium. So here we have compression and equilibrium, right? We know compression is on the left because compression is negative x, expansion or stretching the spring is positive. So this is your negative. Now here you can see that the area under the graph, this would be a positive area. And we're going from left to right, like you normally do on a graph. This would be positive work because you're going from left to right on the graph and the area is positive. Lo and behold, positive work, right? Next, if we want to look at the next scenario, we have the work done by the spring going from equilibrium to compression. So if we look at equilibrium, and then we're going to compression, you're going in this direction. this is going to be a little different, right? So yes, the area is positive. That doesn't mean work is positive, because now we're going from right to left. This is backwards math. So whatever the area is, right? If the area is positive, you're going to flip it to figure out the integral, right? Because integral isn't just area under a curve. You also have to consider, are you going forwards or backwards? Here we're going backwards, so here you have a negative work, and we agreed up here, negative work. Right? All right, so our next scenario, we're going to look at the work done on the spring. Well, let's not do the on the spring, because that's going to be complicated with our graph. Our graph is the force done by a spring. We don't want to look at the graph of a force done by a spring to find the work done on a spring. That's just not going to jive. That's not going to mesh well. It's going to disagree. It's going to get confusing to explain. So let's skip to the fourth one. Work done by a spring from equilibrium to expansion. Okay? So if we go from equilibrium to expansion, we start at equilibrium, we come down to expansion. Okay? We look at this triangle here. Okay? We are going forward on the graph, right? Left to right, equilibrium to expansion. The area here is negative, and since we read the graph like normal, that sign sticks, and you've got negative work, right? Which we agree right there. Great. Just another way to see that the work is positive or negative, just another way to illustrate it. All right. Now, last. Work done by a spring is going to depend on the exact starting and ending position, not just the displacement. So we've talked about this before, right? Work, I'll write down here. Work, okay, is force times displacement, and then you've got the angle between the two, right? Now, that's not going to be the case for springs, and we're going to demonstrate why. So we have a dart gun utilizing a spring, and that K constant is 60 newtons per centimeter, okay, to propel the dart. Now, letter A, it says, is it absolutely necessary to convert centimeters to meters in this problem? Not necessarily. We don't have to. We can just hand settle for newtons per centimeter. If we get work, our work would be Newton centimeters, not Newton meters. If that bothers us, we'll change it. Okay, but it's not absolutely necessary for this demonstration. So first, it asks how much work is done on the spring to compress the spring from equilibrium to 2 centimeters. So to do this, we are going to integrate, right? We want to do the work, okay, work done on the spring. Okay. Work done on the spring. And now remember earlier, let's go back up here. Okay, the work done by a spring is shown by this F is negative Kx. That's the force by a spring. If we look at the force done on a spring, that would be positive Kx. Okay? So as you, for example, if you were going to expand, okay, let's say we're going to stretch a spring, right? This is a positive X, and to do so, right, you have to have a positive force, right? That jives with our equation down here. If you're going to compress a spring, right, you've got negative X, but your force would also be negative, right? So that's how this is. The graph instead, okay, our graph for the force on would look like this, right? With a negative X, you have a negative force, right? Negative X over here, and then you have negative force done on the spring. Then when you have a positive X, you have a positive force done on the spring. So the reason I come back to this, right, is because when we come down here and we want the work done on a spring, we'll integrate positive kx, not negative kx. Okay, and we will. So I'll actually write that over here. Force done by a spring is negative kx, but the force done on a spring, okay, is positive kx. Right? Now, as we integrate this, we're integrating from equilibrium to 2 centimeters, and we're compressing it. So that is a negative, right? Negative distance. We won't actually show that negative on our x though, because our positive, we're just looking at how much is it being compressed, right? We don't have to worry about the positivity, because all of these are asking about compression, right? So force done on a spring, okay? We have 1/2 kx squared from 0 to 2 centimeters. Okay, so if we do this math, we have 1/2, k is 60, and we want to go from 2 centimeters squared minus 0 centimeters squared. Okay, so that gives us 1/2 times 60 times 4. That will give you 120 Newton meters. Okay, I'm sorry, that's Newton centimeters. We talked about that one. So you've got 120 Newton centimeters. So that's the work. Let's go back up here. That is how much work is done on the spring to compress it from equilibrium to 2 centimeters. Now, that was part B. Now part C, it asks how much work is done by the spring. If it's decompressing, okay, we already compressed it from 0 to 2. Now it's decompressing from 2 to 1 centimeters from equilibrium. So let's do that here. Okay, we want work done by the spring. Okay, that is going to be, let's get rid of those vectors. That's going to be the integral from 2 to 1, right? Decompressing from 2 to 1 of negative kx dx. Should have had a dx up here as well. My apologies. Here we go. Now, if we integrate this, okay, we get negative 1/2 kx squared from 2 to 1. So remember, we can flip this and just do 1/2 kx naught squared minus 1/2 kx final squared, because of this negative here. We did this earlier, and I'll just show you doing both ways. Okay, so here if we do 1/2 negative 1/2 kx final squared minus negative 1/2 kx naught squared. Let's go ahead and do both of these. So this would be 1/2 negative 1/2 times 60 times x final, which is 1 squared, minus negative 1/2 times 60 times 2 squared. So here we have negative 30 times 1 is negative 30, plus, what is that, 60, 6 times 2 is 120. So negative 30 plus 120, you get 90 Newton centimeters if you do it this way. Now if we do it the other way, we've got 1/2 kx squared. So we've got 1/2 times 60. Then we have our initial value, which is 2 squared, minus 1/2 60 times our final squared. So here we have 1/2 times 4 is 2, so you've got 120, minus 1/2 60, that's 30. You again get 90 Newton centimeters. So it really doesn't matter which way you do it. I think that this would be a little bit more simple, but it's also just another thing you have to remember. So if you want to just stick to your integral rules and do it the way you've always done it, not an issue. Okay. So that's how, what is it? How much work done by the spring to decompress from 2 to 1. Okay. Now, let's do part D. How much work is done by the spring decompressing from 1 centimeter to equilibrium? So let's zoom in here. We've got D. Okay, we want to find the work done by the spring if we go from 1 to 0. Okay, of negative kx dx, you've got negative 1/2 kx squared from 1 to 0. What we'll do is we will do negative 1/2 kx naught squared minus 1/2 kx final squared, like I showed up above. So here we have 1/2 times 60. Our initial value is 1 squared minus 1/2 60. Our final value is 0 squared, so all of that goes away. So then our answer is 30 Newton centimeters to go to decompress from 1 to 0 centimeters. Now let's look at this, because letter E asks, compares C and D. Does every centimeter of decompression produce the same amount of work? So we decompressed from 2 centimeters to 1 centimeter. Here we decompressed from 1 centimeter to equilibrium, which is 0 centimeters. Okay, it took triple the work to go from 2 to 1 than it took to go from 1 to 0. Which is startling, right? Force usually just cares about the displacement, right? We just, delta x, displacement is 1 centimeter. Here again, displacement is just 1 centimeter. So this is something that's very different for springs. And this comes back to the title of the slide, okay? That the spring depends on the exact starting and ending positions, not just displacement. So if you think about a spring, right, if you just want to compress it a little bit, it doesn't take a whole lot of work. But if you want to compress it all the way down, it takes considerable more work as you try to compress it harder and harder, or compress it smaller and smaller. Same for stretching a spring. If you stretch a spring, as long as you don't stretch it to the point that it ruins the spring, as you stretch it, it gets harder and harder to stretch as it gets longer and longer until you can possibly break it. But that's why springs are different, right? Springs have a special force equation, and they also have a special work equation, because their force doesn't just depend on displacement. Their force depends on exactly how far have you compressed it, or exactly how far have you stretched your spring. So when I said earlier that, oh darn, where did I put that? I mentioned it earlier, I promise. It was when we were talking about integrating. That's it. What can we use to calculate this area, right? We're going to use the integral. And when we do this, you have to use specific variables, right? It has to be a definite integral when you're doing this. If you just try to use a general integral with no idea of, if you just have displacement, but you don't have a starting and end point, it's not going to give you the right answer. I mean, you might get lucky and get the right answer, but don't put your money in that basket. Or I guess don't put your eggs in that basket. So what you want to do for work of a spring is you have to have the start and end points. If you don't have the start and end points, you might need to calculate them, because you're going to need those to get the correct answer. All right, so that's all we have for springs. Next, we'll be continuing on through our work, springs, kinetic energy, and power chapter.